Okay, so this is the second part of the talk that I gave a few weeks ago. Same title. So we want to talk about the Grothendieck period conjecture motives with maximal unipotent radicals. So now, what is it? Why am I not? Why is this slide not moving? Okay, let's do it this way.
Yeah,
okay.
it's moving. Yeah.
Okay, excellent. Okay, so I'm going to introduce the setup first. Can you see my cursor?
Yes.
Yeah, okay, perfect. Okay, so we're going to fix the Tanakian category T over a field of characteristics 0, and we're going to assume that this category is equipped with a weight filtration. So this filtrations are similar to the weight filtration for mixed Hodge structures or a category of mixed motives. And we're going to, moreover, assume that the pure objects, so these are the ones that only have one weight, these are actually semi-simple. So really, for all, it's what I'm going to speak about, sort of the theory is in this generality, but, for all purposes of, in our interest, we may assume that either we're working with the category of polarizable mixed Hodge structures over Q, or any Tanakian category of motives or mixed motives over a subfield of C. Now, even though I'm in this, more general setting, I'm going to use the word motive to refer to any object of my category T. Now, last time we saw that, Tanakian formalism associates to each object X of this category a sub-object or sub-motive UX of this W minus 1 and X. So these underlying ends and underlying harms, these are internal harms in the category. So this is now a motive, and this UX is a sub-motive of that. And this is the motive associated to the Lie algebra of the unipotent radical of the motivic fundamental group of X. So if you fix a fiber functor, then when you apply your fiber functor to this UX, what you're going to get will be exactly the Lie algebra of the unipotent radical of the Tanakian group of X with respect to that particular fiber functor. Now, last time I mentioned that this UX sort of captures the extension data in the subcategory generated by X, and there's various people have worked on this, some names that I mentioned last time. Now, what I'm interested in for this talk is the following questions, and both of these are motivated by Grothendieck's period conjecture. Now, as we said, so this U is contained in here. So I'm going to say that U is maximal, or X has a maximal unipotent radical if exactly this U is equal to this W minus 1N. Now, first question I'm interested in is that, well, when does X have a maximal unipotent radical? And as I said, I'm interested in these motives with maximal unipotent radicals, because of Grothendieck's period conjecture. So if you fix your associated graded, the motives that have maximal unipotent radical, these will have the maximum dimension of motivic fundamental group, motivic Galois group, and hence Grothendieck's period conjecture would predict that they should have the highest possible transcendence degree of periods, field generated by periods. Now, my first question is that, well, how can I, if you give me an X, when does it have a maximal unipotent radical? So some sort of criterion. And the second question is about classification of motives with maximal unipotent radical. So if you give me a semi-simple A, so this is going to be the associated graded. If you give me a fixed semi-simple A, I want to classify all X whose associated graded is isomorphic to A, and such that the unipotent radical and
A maximal unipotent radical.
Maximal, exactly, maximal in this sense, yes. And I want to classify all these X's up to isomorphism of motives. Now,
sorry, Payman, may I ask, like, A is an object in the Tanakian category which is pure, right?
It's not, it's the direct sum of pure objects.
I see. Okay, thank you.
No problem. Now, here, okay, so I'm fixing the associated graded, and I want the unipotent radical to be maximal. But of course, if you remove this maximality of unipotent radical, this question is still very interesting. So I'm gonna have two tasks here for task 2. Sorry, there's gonna be a 2A and 2B. 2A is just you give me a semi-simple A, and I want to classify all X with associated graded isomorphic to A. And my other task is that, well, among these, I want to know, I want to classify the ones that also have a maximal unipotent radical. And there's a little comment here about, this associated graded being isomorphic to A. You can sort of consider this problem in two different, ways. One of them is that completely, disregard the data of this isomorphism. So really just, associated graded isomorphic to A and then X up to isomorphism. And then the second thing is that the second, approach you could take is to somehow incorporate the data of these isomorphisms actually into account. Now, I'm actually more interested in the first problem where, you don't include that data into account, and you're really interested in isomorphism, classifying all X up to isomorphism. But, that's an intermediate question, and this is going to, appear later in the talk. Now,
so Payman
yes.
2A then is basically a question about computing X groups. Is that?
Well, essentially, yes. Yeah. Well, not. It is related to X group, but I'm going to, sort of approach this in a little different way. Still, of course, it's going to be related to X groups, but more along the lines of blended extensions. So that's what the way we're going to be approaching this, trying to basically generalize the idea of blended extensions.
Mm-hmm.
So, sorry, keep going. Here, I'm having a problem with moving between slides, but anyways, okay. So now this is again a slide from last talk. There's a related notion to this maximality of unipotent radicals, and that's the notion of total non-splitting of extensions. So I'm going to recall the definition here. So first is, we'll give the definition in a special case where you're considering extensions of the unit object 1 by some object y. I'm going to say an extension or extension class of 1 by y is totally non-split if for every proper sub-object of y, the push forward of my extension along the quotient map by the sub-object doesn't split. Now, this is a stronger notion than just being non-split, because for non-split, this y prime has to be just, if you take y prime to be 0, this just becomes non-splitting for E, but I want this condition to hold for every proper sub-object. Now, if y happens to be a simple object itself, well, its only proper sub-object would be 0, so total non-splitting will be the same as just being non-split. Now, this was for extensions of 1 by some object. More generally, if you have an extension of some object x by some object y, we're going to say that the extension is totally non-split if, well, first you think of the extension as an extension of 1 via the canonical isomorphism that you have between x of x comma y with x of 1 and this internal harm. And then you would say that your extension E is totally non-split if the extension here, the element here, is totally non-split in the sense that we just described. So it's important that you first think of it as an extension of 1, because otherwise the notion you get will be a weaker notion and won't be as nicely behaving. Now, if X has a maximal unipotent radical, it's not difficult to see that all the extensions that you get by, from the weight filtration on X, so all such extensions, they are all totally non-split. The converse in general is not true, even if you just have 3 weights. But if you have only 2 weights, so, but by the way, when I say 2 weights, 3 weights, what I mean is that the number of steps in the weight filtration. So how many components does my associated graded have? Now, if my X only has 2 weights, then this becomes actually if and only if. So if you have only 2 weights, think about the extension that basically, define, the weight filtration on X gives you 1 extension of a pure object by another pure object. And X has a maximal unipotent radical if and only if that extension is totally non-split. But if you have more than 2 weights, then this is the converse of this is not true. And we're gonna, this is actually one of the key things here in that, maximality in general is stronger than total non-splitting of these extensions. Oops.
Sorry, Payman, before we move on, may I clarify this definition of totally non-split? So you're pushing you're pushing forward along the inclusion of y prime into y. Is that
along the quotients by the inclusion? Yes, along the quotient map.
So the quotient from like y to
Y to
sorry,
I mod y prime.
right. And how should I do you have some mental model for this? Like how are you thinking of this definition?
Well, it's the
Like
strengthening of the notion of being just non-split. So another way to think about it is that to say that your extension is totally non-split is to say, so this one, when you have it as an extension of one by something, to say that it's totally non-split is to say that the extension doesn't come from any proper sub-object of y. So if there's no proper sub-object of y, such that your extension is the push forward by the inclusion map, from that sub-object.
I see. Okay. Thank you.
So you don't get it from any proper sub-object. That's the way to think about it. Okay, so now, okay, so this is from last time. So this was the first task. That was about giving a condition for maximality, a criterion for maximality. In the case of three weights, I stated this result last time, that if you have a motive with three weights, exactly three weights, A1, A2, A3, increasing order like that. Now, suppose that the two extensions that you get, from X of, the consecutive graded pieces. So one of them is the extension of GER A2 by GER A1, and the other one is the extension of GER A3 by GER A2. Suppose both of those two are totally non-split. Now, in general, that's not enough to guarantee that X has a maximal unipotent radical. But if you include the second condition here, that there are no non-zero, so my notation here, maybe I should clarify it here. When I have an underline, I mean the internal half. So that this is a motive, and this is also a motive. But without the underline, that's the home group, for the category, group of morphisms. So now I'm assuming here that there are no non-zero morphisms from this home group to this home group. So here I have the consecutive graded pieces. So GER A2, GER A1, and then GER A3, GER A2. There's no non-zero morphism between these two. It's equivalent to saying that these two motives don't have any non-zero isomorphic sub-objects or sub-quotients. Now, if you include the second condition there, then total non-splitting of these two extensions would imply that X actually has a maximal unipotent radical. Now, we had this example here from last time, that if you, for any odd integer greater than 1 and any prime p, so there's a unique motive, and I'm gonna explain a little, remind you of this, that exists and why it's unique in a couple of slides, but there's a unique motive whose associated graded is this, and such that the two consecutive extensions that you get, one of them is the motive of logarithm of p, and then the other one is a twist of the motive of zeta of n. Now, this result will tell us, because now those two consecutive, harms between the consecutive graded components, this one would be Q1, and then this one is Qn. There's no non-zero maps between them, so this is satisfied, and these two extensions being non-split. Remember, because now you're dealing with simple objects, total non-split and non-split are the same, so this and this being non-split, and the second condition is satisfied, so this will have a maximal unipotent radical. Now, so what's the dimension of the motivic Galois group then? Because for the unipotent radical, you'll now have 3 choose 2 as the dimension, which is so 3, and then 1 for GM, for the the reductive portion. So the dimension of the motivic Galois group is 4. And this is the period matrix. This portion of it is for zeta of n. This portion is for log p. And then there's this more mysterious entry up there. And Grothendieck's period conjecture would predict that the transcendence degree of the field generated by the periods is 4, which is to say that these four, so pi and then zeta and log p and this pi np should be algebraically independent. And then there's a question of, what is this more mysterious period? And that's a very interesting question that we don't know the answer to. Now, yes.
Payman, we were discussing the last time this PNP. This is indeed incredibly mysterious. But do you know even for small n, you don't know the meaning of it?
Well, yeah. Okay. So if you're n, okay. So what makes this more mysterious, Jan, is actually the p. Because if you didn't have the log, this would have been so your motive. You can do this whole thing. Everything I'm going to be talking about in the category of mixed state motives over Z. And then, Brown's work would say that the periods are all generated by multiple zeta values and pi. So this would have been a multiple zeta value. But because of the log, now you have ramification and you're leaving the category of mixed state motives over Z. Now, this would be a mixed state motives over actually Z with P inverted. And now you have this result of the lean that says that, I think if your P is 2 and 3 basically here, 2 and 3, then it will be a cyclotomic multiple zeta value. You have the analog of Brown's theorem. As a matter of fact, the leans was proved before Brown's. But if you have, so if this P is, 2 or 3, then you know what the nature of this. And I think from the, from the sort of the formalism of motivic periods, you can probably even calculate that period. But if your P is other than 2 or 3, I think there's very little known of very little known. Because you don't know, this category, you don't know a generator for this category. That's the problem. If you don't have any ramification, you know that the fundamental group of P1 minus 3 points generates it. But if your P is 2 or 3, you know that now if you remove, basically it becomes a question, becomes about removing mu n, roots of unity. And again, you get a generator for that category that way from the fundamental group. But after that, it's actually known that fundamental group, so of P1 minus 0 infinity and mu n, will not generate the category of mixed state motives or of Z adjoint 1 over n. And so it becomes more mysterious.
So sorry, that's the statement for n bigger than 3, right?
Well, okay, so the Lean's theorem is about 2, 3, 6, and 8. 2, 3, 4, 6, and 8. But now the way I've written it here by just looking at the primes, then yes.
Oh, okay.
Okay, so now I'm going to go to the second task, which was about, the classification of motives with a given associated gradient, and particularly, when you have a maximal unipotent radical. Now, in the case of 3 weights, the key tool is the notion of blended extensions due to Grothendieck. He invented this to study 3-step filtrations in an abelian category. So you've got a filtration like this, let's say, and the quotients, so x1 is a1, isomorphic to a1, and then this successive quotient is isomorphic to a2. This one is isomorphic to a3. Now, this 3-step filtration gives you a diagram like this. So these are all just the natural inclusion and quotient maps. And all the rows are exact, the columns are exact. And now if I choose an isomorphism between the associated gradient and the direct sum of the AJ, the AR, now I can replace these two by A1, this one by A2, these two by A3. And what I will get will be a blended extension of, so it becomes about studying these diagrams. I'm going to go to the next slide. I'm going to formally remind us of the definition of a blended extension. Now, you fix 2 extensions of A2 by A1 and A3 by A2, L and N. Now, a blended extension of N, the red one, by L, the green one, is a commutative diagram like this. This is N, this is L. You put them as the top row and the right column, and such that all rows, all columns here are exact. And then the collection of all blended extensions, I'm going to denote that following Grothendieck GA by xspan and L. This is the collection of all blended extensions. And then, so this is all caps. And then if you just have the first E capitalized, that means the isomorphism classes of blended extensions of N by L, which by definition means that, so when do you say that two blended extensions of N by L are isomorphic? When you have commuting maps between the two diagrams, but the key condition is that the maps on L and N have to be identity to announce two blended extensions to be isomorphic. So this is similar to the situation for X groups, right? So the all cap X means just the collection of all extensions. And then when the usual equivalence for one extensions requires that your maps here and here are identity, right? And that's similar to this, similar convention in terms of capitalization as well. Okay, so that's that. And then there's two key results here. One of them is that so isomorphism class of blended extensions. It's non-empty if and only if this two extension that's in blue vanishes in the corresponding X2 group, Yoneda X2 group. And then the second important result is that when xspan is non-empty, then it will be canonically a torsor over X1 of A3 by A1. So the isomorphism class of blend extensions is canonically a torsor over X1 of A3 by A1. Okay, now going back to the previous example that I had. So here, this is motive of logarithm of P. This is motive of zeta of N twisted. And I want to play the scheme of blended extensions, this as the vertical one and this as the horizontal. Now, by the previous general result, when would you have a blended extension? When does a blended extension exist? When the X2, when X2, as long as X2 of 1 and then this is 0, you're guaranteed that, that X2, that two extension that you had will be vanishing, and then you'll have a blended extension. So here, from X groups in the category of mixed state motives, that X2 of 1 by Q1 plus 1 is 0, and is odd here. Well, actually, X2s all vanish, and being odd becomes important here, but X2 groups vanishing, that justifies the existence of the MNP that we had before. And for the uniqueness portion of it, now remember that we had here that a collection of isomorphism class of blended extensions is canonical torsor over X1, A3, A1. Here you're dealing with 1 and Q n plus 1 and odd. So a group like this, a torsor over this, but that's extension, X groups in the category of mixed state motives. We know that that's 0, mixed state motives over Q. And so that actually unique, what you will have is actually stronger than just unique up to isomorphism of motives, but rather, the picture will be unique up to an isomorphism of blended extensions. So in particular, you get a unique motive up to isomorphism that fits into such a diagram. Okay, so now I will be trying to generalize this discussion. So I want to allow more than 3 weights. Okay, so we have 2 tasks. One of them is we want some sort of criterion for maximality, and the criterion is going to be similar to the one that we had before. Somehow we want to give a situation where total non-splitting of those extensions is enough to guarantee maximality. That's my first task, and the second task would be about classification. Now, focusing on the first task, let's give a definition. We're going to say a motive X with K weights A1 to AK is graded independent, GI for short, if there are no non-zero morphisms between any 2 of these objects. Now, what are these objects? Okay, so these objects here, these are the internal harms between the consecutive graded pieces. So I get K minus 1 objects there. And then I'm looking at, and then this one is now I'm looking at, the internal harms with the graded between the graded pieces, but when they're not consecutive, and always I'm going down in weights here and here. So here, those are for the consecutive ones, and this is for everything else. They're like sum of everything else. And I'm assuming my definition for X to be graded independent means that these now K motives, no two of them have any. There's any non-zero morphisms between them. Now, so a few examples about this definition. If your motive has two weights, it's just automatically graded independence because you don't have this at all, and then you have only one of these. That's it. So trivially will be graded independent. For motives with three weights, this becomes exactly the second condition that we had in the previous theorem. See, because if you have only three weights, okay, so now you have grade 3A2 and then grade 2A1. Okay, so no two non-zero, no non-zero morphisms between them. Of course, there's a third thing here, but now this one would be what? Harm grade 3, grade 1. But by just weight considerations, the weight of this thing is too small to have any morphisms from these ones anyways, in that case. So, you really, when you have only three weights, you can ignore this one. That's it's automatic. And then it'll become about exactly the condition that we had in the previous theorem. And then the condition is guaranteed if your weights are sufficiently spread out. So I have a few examples here. This is the first one. So these pictures, and we're going to formally introduce the theory of basically these pictures. But for now, the way to think about this is that, these one, Q1, Q4, Q9, those are my graded pieces. Okay, so these diagonal ones are my graded pieces. And here I've marked these internal harms between the consecutive graded pieces. So here a Q1, this is a Q3, and then this one would be Q5. Now, if my graded pieces are these four, then my object will be graded independent. Because, okay, so no two of these, there's no maps between them, non-zero maps between them. And now if I look at, everything else, then, okay, so this would be, it gives me a Q4, Q8, and then this one a Q9, and nothing in common. So anything which has these four things as its graded pieces is graded independent. Let's add Q16 also as a graded piece. Now again, this is graded independent. So you've got Q1, 3, 5, 7 as these things. And then everything else that you'll have, there's no way to get any of these ones by looking at harms between any other pieces. But now, okay, so this is also graded independent, but now, oops, wrong direction. This one is no longer graded independent. Now I added Q25 there. Now see, this is Q9, internal harm between these two. And then by looking at 1 and Q9, also I get a Q9. So now this is no longer, this condition fails, right? Here you have a copy of Q9, and then one of these things is also a Q9. Any question about the definition of graded independence?
Yes, so I'm just looking. Perhaps you will come to it anyway. Like this is it would be necessary condition for this maximal unipotent radical, or
no, absolutely not. So you might have maximal unipotence without graded independence also, but this makes your situation simpler. So this assumption will really will simplify the notion of maximality to total non-splitting of the extensions. That's what it does.
I see.
Yeah, very good question. Now, this is the result that generalizes the previous result that we had. So suppose that X is a graded independent motive with K weights, and suppose that each of these extensions between the consecutive associated graded pieces, suppose each of them is totally non-split. Then X will have a maximal unipotent radical. So we're giving a sufficient condition that would make basically total non-splitting and maximality equivalent to each other. And this, if your K is 3, this exactly becomes the previous result. Now, an example for this is that if you have 4 weights, and for the graded pieces are those. So this is related to the picture, my first, when these are the graded pieces. So your motive is graded independent. And then as long as, the consecutive extensions are, if the successive extensions are non-split, you'll have maximal unipotent radicals. So for example, if I take a logarithm, zeta of 3 and zeta of 5 as my consecutive extensions, then I'm guaranteed to have maximal unipotent radical. And we'll come back to this example in the last slide of the talk. So now I'm going to move on to the second task. Okay, so now the second task was about going back to this slide, was about you give me a simple object A, direct sum of pure objects, and I would like to study the classification problem of all motives X whose associated graded is isomorphic to A, and then the ones that have a maximal unipotent radical. And then there's this sort of two versions of this problem. One of them is that you ignore the data of these isomorphisms altogether, and then the other one is that you incorporate those. So now what I'm going to do is that for the next several slides, I'm going to ignore this maximality condition altogether. I'm going to consider this task 2A, and there's 2 versions of this problem. One ignores the data of this isomorphism altogether, and then the other one takes that into account. Let me go back and more formally describe this. So now suppose you have non-zero pure objects, A1 to AK, increasing weights like that, and A is their direct sum. Now we define 2 sets, and they are actually sets because you're in the Tanakian world. One of them, this S of A, is that we're going to look at the collection of all objects X, all motives X, whose associated graded is isomorphic to A. We don't care what that isomorphism actually is. We don't make any choices by isomorphism, just all objects whose associated graded is isomorphic to A. And then we mod that out by isomorphism in our category. That's S of. And then there's S prime of A, which is, now you look at the collection of all pairs, X, and then an isomorphism between the associated graded of X and A. So the collection of all such pairs, we mod that out by the natural equivalence of such pairs. It's sort of obvious notion of equivalence, which is that, it's a morphism, it's an isomorphism from, if I have 2 pairs like that, an isomorphism from X to X prime that exactly, translates this phi to phi prime. Okay, so S prime is about the equivalence classes of the pairs, and then S is just the one that I find more interesting, is really about the isomorphism classes of just objects. Okay, so those are 2 things that we're interested in. Now, if you give me any X with weights A1 to AK, and it gives rise to a diagram like this. Let me explain what this diagram is. So the weights of X are A1 to AK. So let's say for, to make our notation simpler, let's define XR to be, WAR of X. So now you've got a K-step filtration on X, these, X1, X2, blah, 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 like that. Then X0, I'm just gonna, announce that to be 0. So I've got this filtration on X. And now, I get these quotients of, xn by xm, as long as m is less than or equal to n. And I'm going to denote that by xn comma m. So this means xn modded out by xn. Sort of, the obvious quotients that you get from this filtration. And they all fit together in a diagram like this. So what are these ones? You're modding out by x0, that's 0. So this is just x1, this is x2, x3. The vertical maps are all the natural inclusions. So this is x1 sitting in x2, so on and so forth. This last one is xk, which is just x. And then the horizontal ones are all the natural quotient maps. So from here to here, this is x2, this is x2 modded out by x1. So I'm modding that by x1. So the first, the first horizontal map on the, the one on the leftmost is modding out by x1. The second one is now modding out, further by x2 and so on. So these are the natural inclusions, and then these ones are the natural projections. Now, if if you have an isomorphism between associated gradient of x and a, and you choose such an isomorphism phi, then these ones, you can use that isomorphism to replace these ones, the top diagonal, with the AR. Now, the way I'm going to approach the problem of trying to classify, all x with associated gradient being isomorphism to A, both of these classification problems, the way I'm going to approach the problem is by trying to classify all such diagrams. And I'm going to make this, more precise. What I mean, we need a category of such diagrams first, but intuitively, we're going to try to, look at all such diagrams, try to form all such diagrams, and, up to the right notion of equivalence, depending on whether we're interested in this or this. And then the way we're gonna, approach this problem particularly is that, we're gonna go, oops. Okay, the way we're gonna approach this is that we're gonna, to get all the x's, I'm gonna try to, form all these diagrams, but I'm gonna go one diagonal at a time. So I start from the top diagonal, and then I'll look at the second, the diagram right below that, form that, and then so you're gonna complete the diagram one diagonal at a time, starting from the top. So let's look at an example. So all of this is gonna become precise, okay? But just the intuition. I'm giving the picture for k being 4, having 4 graded pieces. So first I start with just the a's. Then I said, okay, so now I'm forming now the diagram right below that. Now, each of these ones, so this would be an extension of A2 by A1. This is an extension of A3 by A2. This will be an extension of A4 by A3. How can I, complete this to this? What are my choices? Well, it would be the product of these x's. And these are capital, all cap x. I haven't modeled out by any relation. This is just collection of all extensions. So that's for the second diagonal. The one after that, okay, so now this is the part that I want us to pay more attention, see what's happening. See, the blended extensions that we had, remember there was the top row, I always been using the color green for those, and the right column I've been using the color red for those. Now this is an extension that's going to sit as the top row, and then this one is going to be the right column. And then how many ways can you fill this portion of the diagram? Would be exactly, the choices are in canonically, in one-to-one correspondence with this all caps x span of x3 1 by x2 0. And if it's non-empty, then it will be a torsor in a categorical sense, it'll be a torsor over all caps x. A3, A1, this is for that entry. And then what about this one? Well, now you have the product of the two expands, and then either it's empty or it'll be a torsor over the product of the two x's. And then what about the next entry? Well, similar game now. Okay, so now this is going to be the top row extension. This is going to be the top, the rightmost extension. And to complete the diagram, you have to choose a blended extension of this extension by this extension. And it's either empty or a torsor over now x A4, A1. So that's how, we're completing these diagrams. Well, of course, we have to model out by the appropriate equivalence, relations. And then we have to also formalize this approach. Any question about these, hopefully this explains the idea, sort of.
Yes, so I have a question. So with this kind of, it look like, is it correct to think about this as an iterative method of these blended extensions?
Absolutely. In a couple of slides, you'll see that. 100%. 100%. Very good question. Thank you. Okay, so now I'm going to give the formal definition. This is what I'm going to call a generalized extension of level k minus 1. So the level is going to count how many diagonals I have below the a's. Okay, so I've got my a's on the number of these graded components is not dropping. That's the nice thing about this construction. I think that, you know, throughout the construction, actually you have the same number of graded pieces. Now, so the k is fixed, and then there's going to be a level that, you know, is going to tell us how many of the diagonals below the a's we're including. Now, the original definition here is about level k minus 1. It's a full diagram like this. A generalized extension of level k minus 1 of A is the data of an abstract commuting diagram of motives of this form. Now, I say abstract because originally we started, you know, with an X in the motivation that sat here, and then we completed the diagram. But, you know, now I'm doing it backwards. You know, all I want is that a bunch of motives, and then included in the data, these structure injections, and then structure surjections, such that I have a commutative diagram like this. Now, of course, if my condition is just that, these motives can become huge. I need some condition to control the size of these things so that this really does become the thing that I'm interested in. And the condition is that such that each of these extensions is, sorry, we don't even know that it's an extension, but each of these things is an extension, is an exact sequence. Now, what are these things? Let me explain this. So these are, what are these things? You start with one of the A's. So my picture is showing it from A1, but it could be any of the other A graded pieces. You start from the, you know, an AR. You go down a number of steps, doesn't matter how many, but then you go right one step. Okay, so now A1 to here, and then to here. This, I'm requiring it to be a short, exact sequence. And then this is for, you know, all choices. So, you know, you could start from any A's, go down any number of steps, but then go right just one step. Okay. And then, you know, you may say that, well, I mean, you're just doing this. Why are you not considering, you know, the sort of the dual extensions that you can have? Why are you not, you know, requiring those to be exact? Those will be actually automatic. So if I go down one step and then go right all the way to an A, automatically that will have to be exact once you require these ones to be exact. So, by the way, exactness of these, it's something that you did have in, you know, in these diagrams. In these diagrams here, you did have those, you know, this, what is this? This is an inclusion of, you know, to go from, you know, this is, you know, A1, you go a bunch of steps down. Okay, so that's the inclusion of A1 here. And then when I go right one step, what am I doing? I'm modding out by A1. So, you know, really it's modeled based on this diagram here. And then, you know, those, these arrows here are part of the, you know, part of the data. Okay, so that's
Payman, just to make sure that the example you had, I understand properly. Like your model example is one where you start with a motive, you take the associated graded, and then you construct this diagram.
correct.
And you know all the pieces already.
That's
when
right.
you do that.
That's right. Yeah, exactly. So for each, you know, each of the motives that I'm interested in, I'll get a generalized extension once, and that's a really good question. Once I choose an isomorphism between the associated graded and A, I will get a generalized extension of A. Okay, so now I'm gonna I have to go a little faster here. Go to you know, to Jan's question. So this is, you know, when your K is 2, you only have 2 graded pieces. Then, you know, a general extension is just an extension of A2 by A1. When K is 3, this is exactly a blended extension. See, so my diagram looks like this. Now all I have to do is to, you know, to make the picture look like my original one. Just bring that down here, and then oops. And then bring this down here, make this one, you know, vertical and this one horizontal. And then the exactness is part of the, you know, is required, you know, you want this to be exact. That was one of the sequences that I required to be exact, right? This is that sequence. And then I required this to be exact. That's now this row, and so on and so forth. So when you have 3 graded pieces, a generalized extension of level, you know, K minus 1 is exactly a blended extension where, you know, but the key thing is that, you know, you're allowing now your extensions to change. So, you know, you have to keep this in mind. So it's a blended extension of an extension of A3 by A2 by an extension of A2 by A1. Okay, so now I want to talk about this level a little bit more, and I already sort of, you know, I guess alluded to it. So the generalized extension of level L in general means, you know, a similar data as before, except that now it's a data of an incomplete diagram, in the sense that, you know, okay, if my level is 1, I'm just including these ones. Level 2, 2 diagonals below the A's, and so on and so forth. Now, by DL, I mean the collection of all generalized extensions of level L. And then, as I said, you know, I sort of want to, you know, go do this, you know, diagonal by diagonal. So you have these natural truncation maps from level L to level L minus 1. All it does is that it erases, or, you know, ignores the lowest diagonal. You have these truncation maps, and there's 2 natural equivalence relations on these DLs. One of them is that you mod out, so this is SL. And remember, you had, you know, this, we had this, in the end, you're interested in this, in this S of A and S prime of A. And what are those? So S of A is isomorphism, so X with associated grade isomorphic to A up to isomorphism, and S prime is about the equivalence classes of pairs like that. Right? And my notation matches that convention here. The 2 corresponding equivalence relations are the following. So the SL is the collection of all general extensions of level L, modded out by just commuting isomorphisms between the 2 diagrams with no conditions. And then the prime version is that your relation you mod is that you commuting isomorphisms. So commuting isomorphisms between the 2 diagrams, but the key condition is that you're requiring that your isomorphisms on A, the top diagonal, are identical. Okay? And then your truncation maps clearly descend to S primes and S and S's. Okay, so I have this, and now my next slide is sort of the main theorem of this construction. So let's recap the notation. I have these SL, S prime L. These are my generalized extensions of level L, modded out by the appropriate relations. And then I have the version of this notation without any index, which is the 2 sets that I'm really interested in. One of them is isomorphism class of X, and then the other one is the isomorphism classes of pairs. Okay, now going to the next slide. Okay, so part A is that you have sequence of maps like that. So these are, you know, the level is dropping. These are the truncation maps. And then, but I'm originally starting with, you know, the set that I'm interested in, one of the classification problems that I'm interested in. So it fits into a diagram like this. And the fibers of each of these maps, so the fiber of truncation, you know, from level L to L minus 1 is either empty or canonically a torsor over the product of these X1 groups. And then this descends. The second part is that now I'm going to really the classification problem that I was interested in. This picture descends now to sequence of maps from isomorphism classes of motives with associated graded isomorphic to A. And then this is for level K minus 1, and then the level keeps dropping. And then here you have the product of X1s modded out by some sort of obvious action of automorphism group of A. Now, this certainly descends to such a thing, but the key thing here is that, you know, we can describe really what happens to the fiber. So you can really describe, you know, what happens, how the fibers descend. I have that as ... here, but it's a precise statement in the paper. But the particular case of it that I want to sort of highlight is that, you know, the fibers above totally non-split elements. So totally non-split generalized extension would be the one that, you know, the corresponding extensions that we had are all totally non-split. The fiber, in going from here to here, descending from this this line to this line, the fibers above totally non-split elements do not change. That's, I think, one of the key nice things about this approach. In particular, on actual isomorphism classes, you're getting these, torsor structures. And then there's a statement, sufficient condition for surjectivity of these truncation maps, vanishing of some X2 groups. And then I'm going to go back to the task 2A that we had, which was about, maximal unipotent radicals. Now, if your A is graded independent, here's what will happen that, okay, so let's say S star is the set of isomorphism classes that have maximal unipotent radicals. So this is, the thing that I was interested in originally. Now, this picture here restricts to this picture, starting now from S star, then goes down. Now you might say, well, there's no, this is an empty statement, but the key thing is the following, that the fibers don't change. Each non-empty fiber of this is again a torsor over that same thing. So I think this is really maybe this is what I think hopefully convinces you that this approach is more powerful than the sort of more obvious approach of trying to just add graded components to your extensions. The nice thing is that this gives me an algebraic structure on actually motives maximal unipotent radicals with the same graded pieces, gives me an algebraic structure on that. And I don't think you will have that, with any other approach that I know. So it gives you a nice way of moving around between those. Now I know I'm running out of time, but I'll take 3 minutes and go back to my example, from earlier. Now we're gonna work with mixed state motives over Q. And the associated graded is this, okay? Now I'm going to play the game that we had. So in the last part of this theorem, in this star version, I'm going to start from here and then work backwards. So for this one, this is just, product of these X1 groups. So I need to take totally non-split. Okay, now, this is my picture, hopefully now is more familiar. These are those generalized extensions, and I'm not, writing the arrows in my pictures. Now, this should be an extension of 1 by Q1, and so up to isomorphism, this would be these, Kumar, isomorphism class of Kumar motives. So the logarithm motive. This one, well, there's actually, because, we're modding out by this automorphism thing. For here, you actually have just one choice, motive of zeta of 3. And then here, motive of zeta of 5. So that's for my first diagonal. Moving to the second diagonal below my graded pieces. Okay, so to complete this one, I have to take a blended extension of this by this. Now, because x1 of Q1 by Q9 is 0, there's a unique thing that I can put here because of the structure that we had on the fibers. So going from here to here, I have no choice. There's a unique lifting. So again, I started with an element here. Here, there's there's a lot of elements, infinitely many elements here. But once I pick my elements here, to lift it here, I only have one choice. So that's now lifted to there. And then now I want to lift that to a full diagram. Okay, so now it's blended extension of this. Sorry, this by this. Okay, so it will be a torsor over x1 of 1 by Q9, which is a one-dimensional thing generated by motive of zeta of 9. So again, I think the nice thing to keep in mind here is that, when I say that, lift to a star is a torsor over this is about isomorphism classes. There's no, I'm not talking about it, also, sort of carrying this particular choice of isomorphism. No, my isomorphism classes will be a torsor over this. And then when I look at the periods, so this portion, okay, so I've got a zeta of 5 here, and then this is, so okay, zeta of 5 there, zeta of 3 here, log of A here, and then these two things, this is sort of, coming from the 3 weights, case, these two entries. But the nice thing is this blue corresponding to going from here to here, adding that corresponds to that entry here. And this will be the period matrix, and then, these have maximal unipotent radicals. So the Motivy-Galois group will be 7-dimensional. So assuming Grothendieck period conjecture, pi, and then each of these entries is giving you one, other interesting number. All of those have to be algebraically independent. And there's two questions here. One of them is that, evaluation of this lambda. And then another interesting question, which I think I know the answer to this one, but I haven't, carefully, written it to make sure everything is fine, but it should work out. The dependence of this lambda to zeta of 9. And, it's a relevant question because, adding that blue, object is, your options are in one, set of objects is a torsor over this. That's generated by zeta of 9. So it is a relevant question. And, how does that depend on zeta of 9? Now, I have one more, I'm going to finish this in 1 minute. There's one other thing that I want to mention is that related to this dependence on zeta of 9. See, here's another interesting result, that if you have a graded independent motive with these weights and maximal unipotent radical, assume that your motive has maximal unipotent radical, then there are no so now I'm looking at the X1 groups in the category generated by X so here I have, a J piece and a I piece, and these are not consecutive pieces. J minus I is bigger than 1. These X1 groups all vanish, and both conditions, graded independence and maximal unipotent radical, are crucial here. Now, going back to my previous example, what this will do is that here, see, in the category generated by X, there's no non-trivial extension of 1 by Q9. So zeta of 9 is actually not in there. So motive of zeta of 9 is not in that subcategory. Now, when you think about Grothendieck period conjecture, what that would imply, if you assume a conjecture, is that if I throw in zeta of 9 in my previous set of 7 periods, that also is algebraically independent. And I'll stop here. Thank you.